Thank you. Hi, everyone. Is everything okay with the microphone? Okay, this is joint work with Danupan Nanonkai, who's sitting over there. I'll announce it again, so I've changed my last name. I went by Krinninger, now my last name is Forster. Hope you find my papers still. It will change in DPLP. Okay, so the topic is shortest path. So here in Paris, the main tool for finding shortest paths is this kind of map. I think all of us have used it at some point in the last days. Having such a map is fine because it's like a really small representation of the graph that we care about. But now we're talking about distributed systems, like huge graphs. We've heard about this in the previous talks. So I'm interested in computing shortest paths in a distributed environment. And it's a single source version where we have a source node S, and we want to compute the shortest paths to all other nodes. Okay, and you might ask, like, this is such a fundamental problem, how can this actually be open? And well, surprisingly, it is. We have very good solutions in the RAM model, we know about this. Then if you look at things, then you realize, well, actually even in the PRAM model, work that has been done like 20 years ago, 30 years ago, this problem, I think, has not been fully understood. Like, okay, everything's recorded, I'm somehow making bold claims about someone understanding the problem, but this is my impression. And now we are working in this congest model, this distributed model, and I would also say this problem is not fully understood. Okay, but I have to be fair a bit. I think also in the RAM model, if you go to something like negative edge weights, this problem is not fully understood. So I think it's fair to say that. Okay, so I said congest model, so I have to define this model. I think this is like one of the unfortunate things about this whole area. We've seen these talks in this session and everyone had a slightly different model, but somehow they all make sense because they highlight different aspects of parallel or distributed systems. And in the congest model, this thing that we want to highlight is that the messages that can be sent between the entities are of limited size. So in general, like this is a model where we want to measure the amount of communication that nodes, that model processors have to make to compute some result of the network, some property or like some function like the shortest paths or distances. And the running time like is the number of communication rounds. So it's just a shortcut of saying, instead of saying the number of communication rounds, we say running time, and we mean something different than in the RAM model. Okay, so formally it's defined as follows. We have processors that are modeled by nodes in the graph. We proceed in synchronous rounds, and in each round, each node, each processor can send at most one message to each of its neighbors, and these messages that we look at have bounded size, logarithmic size, and again, we, at least formally, for now, assume that there is unlimited internal computation power at the nodes between the rounds. So that's the rough model, same as this local model that Mosen has defined before, but with this constraint that the message size has to be bounded by something small. Okay, so just to make sure we're on the same page, so I'm talking about some communication network that's an unweighted, undirected graph, and D is its like unweighted diameter. But I want to solve a weighted problem. So how I have to think about this? I'm thinking about it in the following way. The edge weights are somehow, the edges are somehow annotated with weights, and in our case, even with directions that the paths can take. And we still want to compute shortest path with respect to these weights. So you should think of these weights as somehow costs. They do not somehow represent transportation time of the messages. That's the important thing about this model here. And what's the problem? What's the distributed version of shortest path? It's in some sense an epistemic question. So everyone has this initial knowledge about its neighbors, knows whether it's the source or not. And then the algorithm runs, and the terminal knowledge, what should everyone know, is the distance to the source node, or like more explicit, the parent on a shortest path tree. Okay?
But D is unknown.
Pardon?
D is unknown. The diameter is unknown.
The diameter is unknown, but you can compute an approximation in diameter many rounds, and for this problem we would need diameter many rounds anyway. Okay, simple example. Let's say we're in an unweighted graph for now. What do? We do BFS. It's as follows. So this guy knows he's the source node. He will start, knows it has like distance 0 to itself. What will he do in the first round is send a message to its neighbors that it's at distance 0. The neighbors will learn that they are at distance 1. Next round, these guys know they're at distance 1. They send messages to each neighbors. They receive these messages that can be ignored because they already know the distance, and the other guys know they are at distance 2 now. Okay, finally, they send a message, but it can be ignored. Okay, that's how we proceed in unweighted graphs. This problem is trivially solved by breadth first search. Again, we want to do this on weighted graphs. Okay, so there is a lower bound for this. This is a nice thing about this model. We have unconditional lower bounds, and the lower bound says we need root n plus d rounds to solve this problem modulo polylogarithmic factors that I'll ignore in this talk. Then what are the upper bounds? There's like a very nice algorithm, some parallelized distributed version of Bellman-Ford. You can do it in n rounds. That's really the baseline that we want to have. And then there was this really, I would say, somewhat surprising result of Michael Elkin, who showed that actually you don't need these n rounds of Bellman-Ford. He gave like a nice algorithm that beats this bound. And then other people thought about it. We also started thinking about it, what can you actually do? And these are the current results by Ghaffari and Lee. They get these results, and we get these results. So I know like we would have to like to have like one algorithm that has one elegant bound, but this is the current best we can do. So we have one algorithm that runs in root n root d rounds, and one algorithm that runs in root n to the d to the 1/4 plus n to the 305 rounds. Okay. What's somehow nice about it is these lower bounds also apply for graphs of polylogarithmic diameter, and we match the lower bound with respect to this class of graphs. Okay, in the end, I will say a bit more about why it somehow makes a bit sense. Let me also mention that there has been really a lot of interest in these problems in the recent years. There has been work on all-pair shortest paths, and there has been a lot of work on approximation algorithms for distributed shortest paths. I hope I did not miss any papers. This has been really, there has been really a lot of progress and nice work in the recent years. Okay, so I'll start with explaining our algorithm. I start with like a more general comment. Our algorithm is a scaling algorithm, and if you know a bit about scaling algorithms, they're actually, what you usually find in textbooks is this kind of bit-wise scaling algorithms where you read, like in each iteration of the algorithm, a new bit of the input is read, and something is done, and so on. And we are more like a recursive scaling algorithm. I already wrote like what we do quite concretely, so we somehow compute approximate distances and use those as some kind of node potentials. And this allows us to reduce the maximum distance that has to be considered. So a bit more in more detail. So this is an approach that has been set up by Klein and Subramanian in the PRAM model, and we basically follow their framework. So the goal is to compute some approximate distance. I call it d hat here for each node, and then modify the edge weights. And this is like what I said, this is this potential transformation thing. So you view this approximate distance as potentials on the node, and you modify the edge weight of some edge uv by adding the potential of the node u and subtracting the potential of the node v. This is somehow similar to this Johnson algorithm for shortest paths with negative edge weights, if you remember this. So this potential transformation does not change the shortest path structure, and the nice thing is, now if you recursively solve this problem, what you have gained is that because we have a 1/2 approximation here, the maximum distance we have to consider has halved. So we have to somehow solve a slightly different problem, and if you repeat and repeat, you only need a logarithmic number of steps of these approximation algorithms, solving recursively and doing some bookkeeping to reconstruct the shortest path. There's, however, one catch here. So I can do this potential transformation like with any node potential, but for computational reasons, I want to keep the edge weights non-negative. So I'm solving the case where the edge weights are non-negative in the original graph, and somehow I also want the approximation algorithm that I use here to benefit from the fact that the edge weights are non-negative. And how can this be done? By having this additional constraint. So these are not arbitrary approximate distances, they fulfill like some additional constraint. And this is the following one. The approximate distance for a node V is at most, there's an edge UV, so I always use notation edge UV. So if there's an edge UV, then the approximate distance of some node V is at most the approximate distance of U plus the edge weight UV. So this is some, you could think of it some weak form of triangle inequality. Okay, 2 comments. So if we use the scaling approach as follows, then we are forced to solve a directed problem. So that's why I said, like, you know, we think of the edge weights of having direction. Even if you start with an undirected graph in the beginning, you at some point with this approach need to solve the problem on directed graphs. There's no escape with this approach. And there's some inherent dependence on the logarithm of the maximum edge weight because of this halving of the maximum distance. That's how we could estimate the maximum distance that we currently have in the graph in the beginning, and then it halves and halves. So it would be nice to get rid of this for some reasons, but here we have this dependence, just to make sure you know about it. Okay, so formally, this is the theorem that we use. We have this approximation that is A, like an approximation, and B has this additional constraint that's sometimes called domination constraint. And if we had an auxiliary algorithm that gives us these numbers, then we would solve the problem we want to solve, exact shortest path, just doing a logarithmic in the maximum edge weight number of rounds, plus some book copying work that I'll ignore for now. And our contribution in this work is we designed such an auxiliary algorithm. And naturally, we can now leverage techniques from approximate shortest path. I showed you in the beginning the slide with, there's so many works on this approximate shortest path problem. We use some techniques from there, and then we carefully design the algorithm to satisfy this domination constraint. Okay, the talk has limited time. I'm not doing everything here, so I'll omit that. I'll actually omit the running time analysis in some sense. I just give you some intuition. What are the important things here? We also have to deal with zero weight edges, but it's not a big problem. Actually, you can reduce to this case of positive edge weights if you look at integers. And naturally, our approach gives some faster approximation algorithm for directed graphs, but I'm not talking about it. Okay, so now I'm telling you in a bit like how the algorithm roughly works. So standard technique here, we build some kind of skeleton graph. So let's say this was our original graph, omitting edge weights now because it would be a bit not so nice in the picture to have an edge weight here at each edge. So this is our source node S, and how our algorithm, many algorithms in this field work is we first sample some nodes uniformly at random, skeleton nodes, and the number of nodes is n over h. It's parameterized with some hop count h. So why? Because if we do this, then every shortest path with at most h edges, okay, technically in this talk h over 2 edges, contains one of these skeleton nodes with high probability. Okay, and so what we'll do is we sample these skeleton nodes, then we build some graph between these nodes where the edge weights are the distances between the skeleton nodes. Then we'll, we solve the problem on this skeleton graph. Once we have the numbers, we consider direct shortcuts from the source node to its skeleton nodes, because we can go there now with directly one hop because we know the distance. And then somehow we are left to deal with shortest paths that have at most h edges because of the property here. Okay, this is the rough course of action in a bit more detail, and these are basically now the 5 steps of the algorithm. It's as follows: we sample the skeleton node, we compute the skeleton graph, and here's one slight complication. we cannot compute the skeleton graph exactly because we don't know how to compute the distances between the skeleton nodes exactly. That would already be like a hard problem, but this is now the part where we leverage techniques from approximation algorithms for this problem. We can compute some approximate skeleton nodes where we know the distances between the skeleton nodes up to a factor of 2, some approximation, and we basically set the edge weight in the skeleton graph between the skeleton nodes to a half of this distance estimate. So we underestimate the true distances. And then we solve a shortest path problem exactly on the skeleton. Oh, this is now a black box. I'll say something about this. And then we augment our original graph G to some graph G prime by adding skeleton shortcuts, by adding edges from the source to each skeleton node of the weight that we have computed in this black box step. Okay, and then I'm saying, now just compute the h-hop distances in G prime. So what are h-hop distances? Here I mean these are like the distances you would get from shortest paths that you restrict to using at most h edges. So the best path with h edges, the cheapest path with h edges that you can take, this gives you the h-hop distance. So you can do this by running h iterations of the Bellman-Ford algorithm. And the claim is like this approximation here is the one we want. It is approximate and it fulfills this domination. Okay, short comment about running time. Of course, everything depends on balancing h. So if I would ignore this third step, just steps 3 and 5, then I would get like a root n number of rounds. I could set h to root n. I cannot exactly do it because of this recursive step. Okay, so now I'll give a short argument why this domination constraint is satisfied. Okay, I think the approximation, you have to prove it, but the domination thing is the main part of the paper. This is why everything works, and I'll give a short overview of the proof now. So we need to show this. This is this domination constraint. Okay, now there's one pitfall. I computed these h-hop shortest distances, but they are actually not distances. Like this is a bad terminology in some sense, but people have used it all over the place, so we also do it. Because these distances, these h-hop distances, do not induce a metric. Because if they would induce a metric, I could immediately argue with triangle inequality. So what I'll actually show, h-hops is enough to get the true distance in this augmented graph. And the argument is as follows. So let's look at some shortest path in this augmented graph. The key idea, I think, somehow surprisingly, this was the really important idea. This graph has like a very restricted form. It can have at most one of these shortcut edges, and then it's followed by a shortest path that was already there in the original graph. There cannot be other shortcut edges because these are directed edges, and we have simple paths. So that's it. Okay, and now. Like this is a standard argument now. We subdivide this shortest path into chunks of h over half edges, and we know because of this sampling that with high probability each of these chunks contains one of these skeleton nodes. Now I could like follow these skeleton nodes in the skeleton graph, and because their edge weights have underestimated the true distance, this would be cheaper to go via the skeleton edges. Okay, but these skeleton edges are not there in this augmented graph that I was looking at, but that's not a problem because I've computed shortest paths in the skeleton graph, and in the augmented graph I could therefore like use this edge directly, and it cannot be more expensive than the way that I would have gone using the skeleton graph, and the reason is we have this triangle inequality for exact distance on this recursive graph. Okay, and that's the main reason why I insisted so much on these exact distances on the skeleton graph. We have to compute exact distances. And the remainder now has h edges. This is why this Bellman-Ford h-hop distance works. Okay, so how to get exact shortest path on the skeleton? Two variants. Either we do some version of Dijkstra's algorithm, or we recurse. I just gave you a single source shortest path algorithm. We can use our algorithm. So, and this gives these two different running times. And just some short intuition, why can something like this work? Well, first, computing shortest path, single source shortest path on the skeleton. This is a smaller graph now that we have to look at. So this is intuitively why it can work at all. And computation is a bit different. We need, in some sense, to compute something on the skeleton graph, and we do it by actually performing the individual rounds by broadcasting the messages we want to send via a spanning tree in the original network. That's roughly how our algorithm works. And this is, these steps give different running times. Okay. So I'll skip this and goes directly to the open problems. I think it would be nice to match the running time for shortest path to the one of directed single source reachability. And this is root n d214 plus d. This is a result by Ghaffari and Udwani. And you see our algorithm somehow is nearly there. We have this additional term n to the 3 over 5. I'm asking, please eliminate this. And actually, similarly, it's actually open in the PRAM model to do something similar, match this reachability bound. I also should say all of our algorithms that we had so far, all algorithms for the problem in the congest model are randomized. The question is, can you get deterministic algorithms? So thank you for your attention. That was it.
Is there a restriction on the weights on the edges? My real question is, if not, how can you do that with only the log n bits?
So yeah, I mean, there's this question how you define the model. Like one way of defining the model is saying you can in each round like send one message, and this leads to, if you say, okay, we have a congestion of log n, then the weight must be somehow polynomial in n. Now, if you want to like change this a bit, then it gets a bit tricky, like how you exactly define the model. Okay, it's not. I think it's not so easy to define like an addition comparison model in the congest model, but maybe it can be done formally. It's a bit tricky, I think. Right. I mean, of course, you can like always send like if you're fine with like log w rounds, just to send one edge weight, you could send many messages.
But
But
what I meant is that if the only constraint on the instance is that it's polynomial size, then edge weight could have polynomial bits in length. Poly n bits in length for each edge weight. And then how could you send these weights in log n bits?
but polynomial in n edge weights are fine. Like you have.
Value, the number of bits.
The number of bits. Sorry. Yeah. Exactly. I mean, you can't, right? You can't. You have to like pay with the logarithm of the edge weight. We can talk later. Yeah, sure. Thank you.
Do you really have to avoid negative edge weights? Can you say a little bit about it? What goes wrong?
I mean, in our approach, it's very crucial that we leverage this approximation, these approximation techniques. It's not clear to me how you basically would reduce. So you can reduce the computation of an approximate shortest path to basically something like weighted breadth first search, and it's absolutely not clear to me how you would do this with negative weights. I'm not sure like how. Think of like you want to obtain a pseudo polynomial time algorithm. I'm not sure like how you would do it in a simple way.
So if you assume that the diameter is n to the alpha, for example, then can you tell us for every value of alpha what the best algorithm is currently?
Like, you mean if there are like lower bounds that say you could.
So for example, you have two algorithms now, and I guess for different values of alpha, you would choose.
I see. Like, what's the trade-off? I have written it in the paper, but I haven't memorized it, sorry. Bellman Fort. Thank you.